So welcome to the class. Let me share notes with you. Okay, and try to get them. Okay, because they're getting themselves into focus. Okay. Okay. So today I wanted to talk about, continue about recursive definitions, but now use structural induction to prove properties about recursively defined sets, or in other words, data structures. And there is one more thing that we need to do there, which is that we want to define functions whose domain is a recursively defined set. So, for example, you define a data structure like binary trees, and you want to define some function on a binary tree, like, for example, its height, or it's the number of vertices it has, or the number of leaves that it has, right? Or perhaps you recursively define some subset of a blurry. I cannot help because, hold on a second, because it's clear on my side. Let me try to switch to a different network and see how it goes. We might lose connection for a moment. And maybe a different network is going to behave better on your end. Okay. Well, let's hope so. So, or you define binary strings, some class of strings, and you want some function on them, like, for example, their length. Okay, so we need to do that still. So let's look at the blueprint for recursive definitions that we had. It consists of two cases, right? Like all instances of recursion that we have seen in algorithms, in sequence definitions, recurrence relations, or in inductive proofs. You have a base case. So you declare some elements, let's call them A1, A2, A3, ... as members of the set. These are typically some sort of minimal atomic building blocks of this set, elements of set S. Then you have a recursive rule that says that if some bunch of objects are in the set, then so is some function of these objects. And so this function, I call it const for construction, because typically what this does functionally in this context is that this function takes a bunch of objects and creates a new one based on that, that somehow use these atomic objects, these objects x1, x2, ... And every recursive definition has this form. We have never seen constructions which would use more than two. Okay, and I don't believe that I have such example either in the book or in lectures or maybe in discussions. So for all practical purposes, I could end the bracket right here after two of them. But you see that it's general that, if you want to, for example, define trinary trees that has, every node has 3 children, then naturally you would take x1, x2, x3 would be your arguments here, and you would construct a new trinary tree having x1, x2, and x3 as its children. Okay, and also we have seen cases where there is not just one such recursive rule, right? There's several. So you can, so therefore, really this is construction 1, construction 2. So for example, integers that we used last time, right? The base case, okay, you have many possibilities, but let's say I declare I1 to be an integer, and then I have a recursive rule that if xy is in the set, then x plus y is in the set. And also I have another rule that says if these guys are in the set, then so is x minus y, right? So here, these two guys are examples of x1, x2. This is construction 1 applied to xy, and this is construction 2 applied to xy, right? So simply construction 1 is of xy is a simple function, is x plus y, and construction 2 of x dot y is x minus y, right? So, so here are the examples that you already know, and they are indeed of this form. Okay, so right, the trees we'll come back to that in a second. So now let's say you want to define a function, some function f, whose domain is this recursively defined set. And the range doesn't really matter. So whatever the range is, like nothing is going to change. You know, if I want to have a functions that output Boolean, or I want to have a functions that outputs integers, or whatever, right? So it really doesn't matter. How can I define a function whose domain is this kind of recursive set? Well, like this. Base case, define, somebody's unmuted. Maybe I need to mute you all. Sorry about that. The break, I can do that. I will mute. Allow participants to unmute? Yes, I allow you to unmute. Okay. Oh, okay. Somebody said that view is better, so I'm glad about that. Going full screen helps. I hope I am full screen. Am I full screen for you? I think so, yeah? Yes, thank you. All right, so base case of this definition of f would be define f of x value for all x in the base cases. So a1, a2, ... Simply all base case elements of S. Okay, so like for example, let's say that I want to define some function of integers. So I defined integers recursively using this recursive definition. The only base case is 1. So here I have to declare, you know, let's say my function does this. Let's say I want to have a function that takes an integer and outputs its additive inverse. So what I have to do, I have to say that first of all, on the base case, it is -1. And I'm done. That's that already takes care of this part. Okay, in this case. All right. So let's now see, but that's just the base case. Recursive part or rule, you know, I don't remember what this is called. Maybe the book has some name for it, but it's the recursive part of the definition, is that define f of x for x, which is equal to this construct function on arguments x1, x2, ... however many there are, and please, it's usually no more than 2, right? So usually this bracket ends right here. For other, as some function of f of x1, f of x2, ... So this together successfully defines a function f on all elements of S. Okay, so I will only argue this informally, but in the base case, clearly you define the value of the base case definition defines f value on all elements of S which are inserted into S by the base case. Okay, now every other element of S is inserted by some number of applications of the recursive rule. Let's call this n. Okay, take an element of S. It must be inserted with n applications of recursive rule for some integer n. And let's here is an inductive argument for why this function successfully defines the value of f for that argument. Let's assume that it does successfully define value of f for all elements of S which are created by fewer than n applications of the recursive rule. So by that assumption, when you are defining the n, this element x using n applications, all these guys here must be already in set S, so they were defined using n-1 or fewer instances of recursive rule. And therefore, by the inductive assumption, the values of f on all of them are well defined. And because you define f of x as some function of these, so therefore this function is well defined because all its arguments are well defined. So therefore, this will define the value of the function at point x. Okay, that was a lot of okay. I wanted to say mumbo jumbo, but hopefully not exactly a mumbo jumbo. Let's see it in operation, right? So you have this recursive definition of integers, and we defined the value of the function. So we want to define this for all integers. Case 1, we define it for the base case. Case 2, well, how shall we define it? Well, how about this? F of x plus y is minus f of x. No, it's actually minus fx plus f of y, right? Because if this is indeed minus x and this is indeed minus y, then this whole thing is minus x plus minus y, which is successfully minus x plus y. Okay, so I am doing what I was supposed to. This the first recursive rule defines puts x plus y in a set if x and y are in the set. So I have to define what is the value of this function on this guy here. Well, that's x plus y. So let's define it as some function of the value of the function on these arguments. You know what? Maybe it would be better if I mean, this is going to be ugly looking, but just for consistency of the notation here, I will do this. So this is x1 and x2, and this is x1 minus x2. Okay, and now there will be better consistency of the notation. So this is minus x1, this is minus x2, minus x1, minus x2, and minus x1 plus x2. Okay, and because I have one more recursive rule, so this was really my first step for recursive rule number 1, but I need another step for recursive rule number 2. And what was that? That was this. So I need to define f of x1 minus x2 as some function of f of x1 and f of x2. So that would be probably this one. Let's check. This is minus x1 minus x2, right? Because I'm assuming that the function was successful on all the arguments of this construction. The construction is x1 minus x2, okay? So let's see, right? So what is this? This is minus x1 plus x2, and that is minus x1 minus x2, okay? Which is correct. Any questions? This perhaps was not such a fascinating example, but it's it illustrates. It gives you one illustration of this concept. Let's do another one. So here is our blueprint, and now recall a definition of what was it called? Just binary trees, I call them, from last lecture. And that was, I believe, the base case was that an empty string, I declared it to be a binary tree, and then a recursive rule was that if two trees are, if I have some two binary trees, then for all A, and this is in some implicit universe, because I can have tree of bits, tree of bytes, tree of strings, tree of whatever. The following thing is declared to be a tree as well, and it is something that looks like this: A with left child, whose left subtree is T0, right subtree is T1. Sorry, I will close the door. Sorry about the noise. Okay. So there was our definition, and we looked at what kind of binary trees it constructs last time, right? So let's now define something for it. Okay. What did I want to define? Height. Okay. So let's define height, or you can call it of a binary tree. So I will have a function h, which takes the set of binary trees and actually gives natural numbers out, right? The height will always be a natural number. And what do I have to do to follow the, but notice the domain is this recursively defined set, which in this case is a BT, okay, set of binary trees. So base case, I have to define the function. So here, the capital F in my case now is this H for height. So I have to declare it for all elements which are inserted into BT set by base case. But that's very simple. There is only one such a thing. It's an empty string. And, you know, I will not surprise you, I think, by declaring that an empty string has a height 0. Okay, all right. What is the recursive part of this definition? Okay, well, I have to define the value of the function, which in my case is h, of any element constructed from the previous one, from some previous elements using this recursive formula. So what is in my case? In my case of you know, the only recursive rule, bunch of xi's are in the set, then so is some construction using the xi's. That's this one. The xi's are now called t0 and t1. So I have 2 of them. And this is the construction. So it's a function that takes some extra element a, right? So as I was saying, you know, what really, if you really want to think of this way, then there is like some added argument here that have nothing to do with the set. S, there's some external elements, right? Some constants. That's what this little a guy does. Okay. So the recursive rule is that you have to define h on t for t which is formed by using this recursive rule. So this x here I call t because it's a better variable for members of the binary tree set. And the only construction is this construction. Okay, it's the function that took 2 trees, t0, t1, had some constant a, was indexed by a constant a, and created this object. So I have to define this ht for t1, okay, i.e. h of this object. I will, and I don't have space. So you have to define this, okay? So we will, h of this object will be, well, think about this. What is the height of the tree? It's the, let me see if I have some pictures. I do, but I don't know where. It's the, if this tree is short and this tree has a big height, the height of the whole is just going to look at the height of this and add one more. Okay, so let me just cut to the chase. It's the max, it's 1 plus the max of the height of t0 and the height of t1. So the maximum function takes 2 integers and outputs the larger of them. Okay, so max of xy is defined as x if x is greater or equal to y, y if y is greater than x. Okay. And I'm done with the recursive definition of a height, right? Because that's the only recursive rule. So that's the only recursive case I have for the height definition. Let's see how this how this recursive definition of height operates. So, okay, so let's draw some tree. Okay, let's. So I have let's these be subtrees. Let's say he doesn't have here, but he has EF, and this has GH, and this guy has two trees, IJ, two subtrees, and there's nothing here, but this guy has KL, and this guy has M and N. Okay, so how did this tree become constructed? Well, in the last move, there was some subtree rooted by B, that was T0, and rooted by C, that was T1, and you created this whole thing. And this one was created by T0 was this, T1 was an empty string, and so forth, right? So now, how do you use this height function? Well, you have to use it sort of in bottom up, because the height of this tree is defined as a function of the height of its subtrees. So you have to know the code that computes the height of this tree would have to first compute the height of this one and the height of this one and take a maximum. And then you recurse, right? So what are the bottom cases where this tree will be defined? This is actually not a base case. The base case is an empty tree, but that everybody here has two children was created by the recursive rule by taking two empty subtrees and adding it to a single vertex, right? That's how we created, this was created as a tree. So a leaf is not a base case yet, right? The base case is an empty tree. So really, these are all base cases. The base cases look like this. This kind of manic, but I have to do it for illustrative purposes. Okay, and now I have the complete derivation. And now, what this? How did this recursive? How did this recursive definition now compute height? Well, all of these have height 0, right? All of these guys have height 0. Now, what about this guy? Height function. He's not the base case guy. He's created by taking two base cases, okay, two subtrees, and these are the T0s and T1, and their height is already known, it's 0. So to compute the height of this guy, I take a maximum, I take a 1 plus the maximum of 0 and a 0, which is of course 0, therefore the height of this guy is 1. And by the same argument, everybody in this line, their height is gonna be 1. Okay, I cannot evaluate the height of this guy because the left subtree T0 for him height is defined. The right is not yet. Okay, so the next level that I can define height is these two. Okay, because their subtrees are both, all height is defined for them. Let's look at this one.
Sorry to interrupt, but you kind of cut out for everyone. Could you go back to when you drew the first level? Could you explain from there again?
So, okay. Well, I'm not sure where I lost you, but where it was cut out.
Right when you drew that line with cutting out all the empty.
Yeah. Well, so basically, the height of all these guys is 1. The height of E, G, H, M, N, and L is 1 because it's the same case of recursive argument. What's the height of E? Okay, so let's draw this case. Let's zoom up on this case. This is a T, this is a T0, this is a T1. sorry, or this is, I called it A in this recursive definition. And this whole thing is a T, right? So it's a case of creating a tree T from some vertex A, which in this case is E, and some subtrees, T0 and T1. Both of them are empty. And now height of this one is 0. Height of this one is 0. So when I define a height of this one, so h of lambda is 0, h of lambda is 0, h of t is 1 plus max of 0, 0, which is 1. Okay? So this definition successfully defines the height of this tree as 1. Okay? And it's exactly the same argument for all of these cases, right? Nothing changes except of the constant, which is E, G, H, M, N, L in all these cases, right? Okay, let's now look at subtree rooted at F. So here I have a subtree rooted at F, and I'm putting it, I'm forming it by these two so this is now my T0. This is my T1, and this whole thing is a T. And now height of this, the height function mapped it to 1. The height function of this guy mapped to 1, right? So the height of G was 1, the height of H was 1. Therefore, the height of this T will be, what is the definition? 1 plus max of 1 and 1, which is 2. Okay, so these guys will be the same way, right? So sorry, so everybody here had height 1, everybody here had height 0, and these guys have height 2. Now let's look at oh yeah, and so this guy has a height 0, this guy has a height 0, this guy has a height 1, right, by the same argument as here, and I cannot evaluate further because this guy I cannot evaluate. I know he's left, the height of the left subtree. I don't know the height of the right subtree. So, okay, the next guy I can evaluate is this. So let's look. I have a D, which I put E and F, GH. So this is a T0, a T1. This is a T0, and the whole thing is a T. Okay, now E, the height function assigned 1 to this subtree. The height function assigned 2 to this subtree. So what height function will assign to this whole thing? It will assign 1 plus max of 1 and 2, which is 2. So therefore, this is 3. Okay, and it's good, right? Because the height is 3. 1, first level, second level, third level. So that definition seems to work. Okay, and the argument for this guy will be the same with the flip. So in his case, T0 has height 2, T1 has height 1, and so that you take the max, and it's 2. So therefore, this guy will have height 3 as well, right? And here, this will be T0 has height 1, T1 has height 3. So here is 1 plus the max of 1 and 3, which is 3. So this guy will get height 4. This guy also will get height 4. His T1 for him is height 0, but T0 is height 3. So this is 1 plus the max of the 2, which is 4, and the final thing aside height. So these are the 4, right? And here are the tree. Okay, that's how this that's how this function, successfully defines height of every binary tree. Let's look at another example. Okay. Where is my stuff? Hold on a second. I got a little lost in my own notes. Okay, they're here. Okay. Define a vertex count function of BT of BT. So there is some VC. I call that function VC. It will take any binary tree and assign an integer to it. But now I want this function to express the number of vertices in a tree. Okay. And where was my blueprint for all recursive definitions was here, but I guess maybe I cannot fit it. But I'll try. So the base case for the vertex count is, well, again, the blueprint, I have to just define what is the vertex count of the single tree that is injected into the set of binary trees by the base case. This is an empty tree. And, again, no surprises that an empty tree has no vertices. So the count of vertices is going to be 0. Okay. And okay. And what about the recursive case? Well, the vertex count, again, my recursive definition is so concise. There is a single base case and a single recursive rule. And in a sort of really surprising, I believe, fashion, it generates these complicated objects. And recursive rule, therefore, has to be just done for the single thing that is injected into the tree family by the recursive rule. So I just have to define what's a VC on this type of tree as a function of the vertex count on T0 and T1. And what is it? Well, however many vertices are in this subtree should be added to however many are in this subtree, and then one more for this root. So it should be 1 plus the vertex count of T0 plus the vertex count of T1. And I will not have time right now to go, how that this successfully defines the vertex count, but you can check that it will, right? Like you use the same binary tree and the same climbing up the subtree, right? All the subtrees is going to define this correctly, right? Okay. Now the final thing, and I'm a little bit panicking because I only have 10 minutes left and a pretty big thing to cover. But I'll try, and if I don't finish, then I will just continue talking to either those who may stay or to an empty room, and then you will hopefully listen on YouTube, right? I mean, it's better than just cutting it without finishing. So I apologize for that. What is the okay? So now, say you want to prove that some predicate P holds for all x in this recursively defined set. Okay, that argument is use structural induction. And the structural induction will follow exact same blueprints that we already know. And its blueprint is as follows. First of all, base prove that P of x, this predicate holds for all x in the base case set. Okay, so these are all elements in the base case that are injected into the set by the base case. Second, the recursive, or I guess this would be called the inductive step, is that proof that if P x1, P x2, ... if predicate holds for all elements x1, x2, ... then if all of them hold, then so does P with this predicate on the output of this constructor operation applied to these elements x1, x2, etc. So that it holds for P of x, where x is built using this constructor applied to x1, x2, ... Okay, so you see the blueprint is extremely similar, and basically it is maybe a scary name, structural induction. It's scary for me because I can hardly pronounce it, but really it is a standard induction, or rather a strong induction. Where is the strong induction hiding? You can cast this argument as a strong inductive argument on the predicate that takes not elements, but integer. And the predicate says not that something holds for x, but that it holds for all values of set S that were injected into it by no more than n applications of the recursive rule. So therefore, this assumption says, in the inductive step would say, for whatever your point k of induction is, all the if the predicate holds for all elements in the set which are created by k or fewer applications, then so it does for an element who is constructed using k plus 1. Because this x, if xi's are created by k or fewer, then x is created by k plus 1 or fewer. Okay, I'm trying to render this as a case of the standard induction. Maybe it's more productive if I use the almost no remaining time into showing some example of such proof, right? Okay, so here was my, I think that I will have to copy this stuff so that it's all on one page. Okay. Okay, so this is a copy. Binary tree definition, base case, base, lambda is a binary tree, recursive, that if T0, T1 are a binary tree, then something that looks like this is a binary tree. Okay, that's a recursive definition of binary trees. Now I have a recursive definition of a height function. Okay, and that worked like this. Age of an empty tree was 0, and a recursive that age on a recursively defined binary tree was 1 plus the max of height of T0, height of T1. Okay, now vertex count definition was based vertex count on empty tree is 0. Recursive vertex count on a recursively defined tree is 1 plus the vertex count of T0 plus the vertex count of T1. Okay, now that so far that was a copy of what we had before. Now I want to show a proof of the following claim. For all binary trees, I want to claim that the vertex count on a tree T is at most 2 to the height of the tree minus 1. So in other words, if I have a tree of height n, the most vertices this tree can have is 2 to the n minus 1. And that's the claim. Okay. All right. That's my predicate. So here, this is the predicate on the trees, on a tree. Okay. So it is exactly of this form. Okay. It's some predicate that I'm claiming applies to all elements of the recursively defined set. So let's use this blueprint to prove it. Okay, first I have to prove that it holds for all base case elements, but I'm lucky there because I basically have to prove that P holds on an empty string, an empty tree, because that is my only base case, right? So let's see what this says. It says, i.e., that vertex count on an empty tree is upper bounded by 2 to the height of an empty tree and minus 1. Okay, now I look up the recursive definition of H and the recursive definition of VC, and I know that H of an empty tree is 0. So this is a 2 to the 0 minus 1. And I know that VC of an empty tree is 0 as well. So let's evaluate this numerically. Well, this is 1 minus 1, which is 0. And no, 0 is upper bounded by 0. So P of empty tran is true. Okay. And that ends the proof for the base case. And now the recursive step. Okay, the recursive step, what is it supposed to, recursive or inductive? Okay, sorry, inductive. Because it's a proof by induction. They are so similar, then I'm afraid I confuse the two. So inductive step has to argue that if the predicate holds on building blocks, then so it does on the construct. What is the only construct, recursive construct, is this one. So in the inductive step, I have to prove that P holds. So on a tree constructed this way, if holds, prove that this holds if P of T0 and P of T1 hold. That's what you have to prove in the inductive step, right? Because that's what this says right here. It's this instantiated for the case of the recursively defined object that we have here, which is binary trees. Okay, So let's prove it. First of all, let's parse what this says. P of A, that predicate P holds on this thing, is to say that VC on this tree is upper bounded by 2 to the height of this tree minus 1. Now, what does this say? This says that VC of T0 is upper bounded by 2 of height of T0 minus 1. And this thing says that VC of T1 is upper bounded by 2 of HT1 minus 1. Okay, good. So we will use it. Can we use it right now? Not quite yet. Well, let's see. But what is the next step? So I know what I have to prove. I have to prove this thing. This is what I have to prove. Okay. Well, do I know what the VC of this recursively defined object is? Yes, I do. It's right here. I'm going to use by the recursive definition of VC. The VC here is 1 plus the vertex count of T0 and also vertex count of T1. So I can express this as 1 plus, sorry. I can see, sorry, okay, thank you. 1 plus VC of T0 plus VC of T1. And I have to argue that this is a lower, at least, what is 2, where what is height of this thing? Well, I look up the height of defined here, and it is this. So I replace it by 1 plus the max of h of T0 and h of T1. And this I can do by recursive definition of height function, right? I replace this expression by this one. And let's not forget these things. So this is what I have to argue. Okay, but now perhaps I'm in good shape, because what I can assume looks very much in play in here, right? Okay, so let's try to argue. This is my goal. This is what I need to argue still. It is not done, it is the goal. Okay, so let's look at the left-hand side. VC, 1 plus VC of T0 plus VC of T1. Now, by the inductive assumption, VC_T0 is upper bounded by this thing, to H of T0 minus 1. Sorry, I forgot 1. So I have to copy 1. And VC of T0 is upper bounded by this. So this is 2 to H of T0 minus 1. And VC of T1 is upper bounded by this. So this is 2 of H of T1 minus 1. Okay, this is great, because now the constants start working correctly. 1 minus 1 minus 1 is minus 1. So this is 2 HT0 plus 2 HT1 minus 1. Now this looks very promising, because now I have something that looks closer to this. What do I want? I would like the following to be true, that this sum is upper bounded by this. Well, let's see if this is true. This thing is upper bounded by 2 times the max of these 2 things. And I copy minus 1. Why is that? think of this as A and this is B. A plus B is upper bounded by twice the maximum of A and B. Yes, it is true, right? So what I'm using is that A plus B is upper bounded by 2 times the max of A and B. That's the law, I mean a simple arithmetic fact that I'm using here. Okay, and now I'm almost home because this is equal. What is the max of 2 to something and 2 to something? It's 2 to the, this expression is 2 to the max of the exponents, h of t0, h of t1. And let's not forget the -1, right? Because, so that's another law, quote unquote, right? That 2 to the I, that the maximum of 2 to the I and 2 to the j is 2 to the maximum of I and j. Okay? And now I'm really home because this is 2 to the 1 plus the max of h t0, h t1 -1. And now finally I look up that this is indeed the height of this tree. So, well, I already knew that. Yes, so done. Okay, ask me whatever you want of this proof.
So will generally every problem be dependent on several different definitions for the construction?
It might. Yes, although some examples it will only have, so there is at least 3 things at play, right? I mean, okay, there might be simpler examples. There might be examples where you will prove some properties that are not dependent on some functions of the object, but they're just properties that are dependent on the objects themselves. Like there is no extra functions. Okay, then this part falls out. Okay, perhaps you will have some properties that depends only on one function. Okay, then it will be simpler case in that instead of some 2 recursively defined functions of this set, you have just one. So in the discussions, I think that the TAs will cover other examples of recursively defined functions on objects, and I think they will do so for trees. They might do this for other data structures as well. Is there other questions I can help you with this? What was used here, and if you got lost in this proof, then you can, I guess.
Professor?
Yeah.
So you stated the inductive assumption towards the right where you circled VC of T0 is less than or equal. Is that the inductive assumption?
Is that a what?
Is that the inductive assumption?
Yes, because the blueprint for the inductive proof that you are allowed to assume, yes. So basically these are all inductive assumptions. Yes, that your predicate holds on xi's, and now in the inductive step you're proving the following: if the predicate holds on xi's, then it holds on the recursive output of the recursive rule applied to the xi's. So in our binary tree case, if it holds about this T0, T1, then it will also hold about this recursively defined one. So these are our inductive assumptions, indeed. Other questions?
And to the left of what you circled, that's just showing what you want to prove, correct?
Yes, this is, the goal. And this is goal, modified. Right? So, because by recursive definition of VC and by recursive definition of H, I can rewrite this goal in this way. And now I'm proving it.
Professor?
Uh-huh.
I was wondering, what's the difference between structural induction and normal induction? Because this to me kind of just looks like normal induction.
Yes. The short answer is that normal induction is defined for predicate must be and predicate that holds for integers. The predicate in normal induction is always a predicate about integers, right? Let's call them n. And the way you proved it is that if it holds for some integer k, then it holds for integer k plus 1. There is no integers here. There is no such thing, right? Like this is not a predicate about integers. It's a predicate about trees, right? My predicate here is a predicate about trees. That and for every tree, VC of the tree is upper bounded by 2 to its height, -1. So it's just structurally not, I cannot use standard induction because it's, where is my induction variable? Where is my n? It's not here. What I was saying, however, is that you can cast it as a standard induction because there is a hidden variable n. The hidden variable n is the number of applications of the recursive step when you create an object. Okay, so well, okay, maybe I'm just confusing people rather than clarifying anything, but I mean, maybe I'm clarifying for some and confusing others. I can try to make it more formal on a Piazza post.
Okay, so basically, structural induction is just a more general way of induction rather than using numbers specifically.
Yes, you can think of that this way. Yes. Mm-hmm.
Okay.
But basically, for our purposes, if you have a set, some domain that is defined using recursive definition, then if you have some claim about objects in this domain, remember, we had recursively defined examples of like bit strings of all sorts, properly nested parenthesis strings, integers of different types. Yes, we have many examples of these sets that are recursively defined, and they're not consecutive integers, okay? In order to prove something about them, you will use this blueprint of structural induction. You would use the blueprints that if the predicate holds on the atomic xi's, then it holds about whatever is produced by the recursive rule, in this case, this construct here. So it will just syntactically look very different from standard induction, but in spirit, it is very similar, right? And in fact, it can be cast into it, but yeah, but it's structure. I mean, syntactically, it's different because it's not the recursive variable, the variable of induction. Sorry, it's not an integer. It is some object that belongs to some set. It's a data structure, like a tree. Tell me more.
So can we assume that all binary trees take these, like their basic, for example, the binary tree definition, height definition, and vertex count definition? Unless told otherwise, we should just follow what we've looked at in lecture.
You know what? What you said just rings some alarms for me, because I hope to get to it, which I obviously didn't, to a warning that I'm not sure that I asked the TAs to get to it, but I'm not sure they will. Here is my definition of binary trees. It's base case, recursive step. In the book, there is a very similar construct for something the book called perfect binary trees. It's extremely similar, but it differs in the way the recursive step is defined. And and basically it generates completely different objects. We have seen this, we have talked about this, like if you define properly nested parentheses strings slightly differently, use a slightly different base case or a slightly different recursive rule, you end up generating different class of objects. That is also true for binary trees. We'll see actually 3 types of binary trees. There are just binary trees defined here. There are something called perfect binary trees defined in the book. They differ in this step, the recursive. And if I make a slight twist in the base case, that simply I don't declare empty as a binary tree, it has to be some non-empty vertex. But the recursive is the same. Again, I'm defining different class of trees. Like certain trees are not going to be generated that way. So no, this is not set in stone. You will see 3 cases of very close definitions which end up producing different objects. And part of the class is there's no point like memorizing this rule. The point is to understand how to use such rule, what it defines, to get in your head and to produce stuff on this sheet of paper so that you can see what class of objects is created. And part of the point is that these things are incredibly sensitive to the base case as well as to the recursion rule. And any slight changes in these might generate the different class of objects. Likewise, height. Well, I guess there is no variability here. I mean, the only reasonable way to define it is this. And the only reasonable define it is this. I mean, if my in a class of objects, I don't have empty, I only have non-empty trees, then I guess it's a part of my own, do I want to define a height of a single vertex as a 0 or as a 1? Okay, both would be reasonable. And then they would change, whether a claim like this is correct. You would have to adjust for, using proper constants here.
And Professor?
Yeah.
For like exam questions, would it kind of be like part A, you write like the definition, like your definition for binary tree, then part B, you write the second definition for like the height. And so basically you would be using your definitions, right? Or that you guys could just give us the definition and then we do it, right?
Look, yes, I see what you're asking. We will never assume that you remember some definition like this. If we ask you to prove something about some recursively defined object, we will give you the definition exactly what we mean, right? Because they are very sensitive to tiny changes. So that would be completely unfair. But you should be aware that these things very much depend on these tiny differences. So for example, if you during the exam, you just try to copy some solution that actually argues this very similar thing, but for an object that is slightly differently defined, you might be completely off. right? So in the homework, you practice these things. You recursively define things, and you see how to argue something about them. Okay. It's also fair to say, like, we will define some recursively defined, for example, tree, and it will ask you to define some reasonable function on the tree. You know, perhaps height, perhaps something else, perhaps like a balance. You know, I can define a balance of a tree as the difference between the height of the left and the right side. Okay, I don't know. Perhaps I can well, the example I think some of the TAs will do is I can define leaves of a tree and count the leaves of the tree and count the internal node. So if you take a tree, everybody here is a leaf because he doesn't have children, and everybody above is an internal node because he, you know, you define internal node as a node that has children, and a leaf as a node that doesn't have children. And there is some very nice relations between number of leaves and a number of internal nodes. Okay, so some of these will be discussion exercises, some of them are book exercises, some of them are homework exercises, and some of them will be on the test.
Okay, thank you.
Hey. Okay. Shall we call it quits, or do you want to ask something else? All right, I see people are leaving. So goodbye, everyone. Till next time.